So right now, I want to show you what is this one. Okay, so that is our step one. Step one is if we are able to determine the shape of these functions, then the remaining simply duplicate the shape, but with certain operation in the time delay. That's it. Okay, so that is the step one. So step one, we're focusing on this one. So let me get rid of this one. So for the step one, we want to solve for these functions, and let me give the name of this function. Let me say, give a name, then call it GT. Okay, and the GT is the symbols used in our textbook. So we want to know is what is GT? Okay, GT is the response of the vibrations to such a small strip. And right now I want to give a name to this strip. And actually in mathematics, the strip is called the impulse functions. Okay? And that is the definition in the mathematics. The impulse function basically is such that certain pulse applied in no time, basically in theory, delta t approaching to 0. Okay? And for any impulse function, its magnitude equal to the area of the strip. So that is the definitions of the impulse functions. Okay. So for example here, if you remember, this is our ft, right? So basically here we can determine the magnitude of such impulse function, which is equal to this number equal to f0, right? So this number is the value of this function at time equal to 0, so f0. So its magnitude equal to f0 times delta t. Per the definitions. You good? Okay. Any questions? Okay, so right now I introduced what is the impulse functions. Sometimes the people talk about is called the unit impulse functions. So what is a unit impulse function? That means its magnitude simply equal to 1. Okay. So that means this is a functions. So that is an impulse function here. Okay. So just like here, we define the unit impulse. That means this area equal to 1. And for my descriptions, I want to have the description is more generic. So that means this step, unit impulse function, usually we using delta t. Okay. So in this way, by introducing the unit impulse function in this way, this impulse function, for this case, if you like to describe in mathematical using our symbols here, then you can describe it is into this. So this one will be equal to this pulse function simply equal to f0. That is the magnitude Okay, so this is the magnitude times delta t. If you like to have input into the function, the name here, you can use this description. This simply is a magnitude. So right now I want to solve for this one and using the generic one. So here let me deal with this case. Okay. So right now I want to solve for is these conditions. Okay, and for this one, let me rewrite. So basically this one, let me divide the equations by n. So x double dot plus c over m, x dot plus k over m, and x equal to m 1 over m times delta t. Okay, so that is the definitions. And for this one, that is equivalent is x double dot plus 2 zeta omega n x dot plus omega n squared x equal to m delta t. I personally, I'd like zeta omega n notation than c and k. Okay, but so every time I try to start from here. So this is our problem descriptions. And right now, I want to talk about the very important, the key step, I would say the key concept in solving a system response to impulse. Physically, when we give an impulse to a system, I think this table I can demonstrate. It kind of weird. So this is the system with the damping, and impulse is such a way, like this. Of course, my operation of my kick is not fast enough. If I kick that quick enough, you can see the impulse applied to the system will respond by do some movement. But if you imagine when at that moment the impulse applied, actually the system is in game of the change in the initial velocity. Good? Okay, so keep this in mind. Let me rewrite the word. When a system is subject to a unit impulse, its velocity, in particular initial velocity, change. Okay, so basically that is basically that can be explained by this. The change in the momentum equal to the integrations of the unit impulse over time. Time equal to 0 to infinity. So this is a force. We integrate the force operation over time that gives us the change in contributing to the change in the momentum. So for this case, the mass of the system is m. And because the delta t applied at no time, so basically the change in momentum is v, and that is 0 plus just right after the moment, and minus v, and 0 minus, that means before the kick. The 0 plus means after the kick. Okay. The integration of the impulse over time, again, this is a unit impulse, and that basically, what is this? That is a function over time. Basically, integration telling is the area under the curve of a function, right? If you remember, in general, if we have any f of t, if we operate f over t over dt graphically is equivalent to calculate the area under the curve of the function. So basically, this integral tells us is looking for the area of the impulse, which for our case, unit impulse that equal to 1, right? Okay. So, and furthermore, and for the system that is stationary, so before kick, the system have no velocity. So after kick, the system gains the velocity v 0 plus equal to 1 over m. So that is the velocity be gained by the system due to the kick. Okay? And this is for unit impulse. So here, if we deal with is a unit impulse, so that is equal to 1. If the impulse is not unit, for example, if we have such a magnitude, you simply scale this number with whatever the magnitude you're dealing with. Be okay? So right now, let us deal with the unit impulse. So under these situations, let me continue to write here. So the impulse applied to the systems, then after no time the force is gone, the system becomes like this: x double dot plus 2 zeta omega n x dot plus omega n squared. That is the same description. Right now, again, I applied, and after the delta t, the force become to 0, but the system's velocity become 1 over m. This term is due to the gain of the velocity, the change in velocity due to the absorption of the impulse. That okay? So for a system, subject to the impulse, and initially x0 for the system that is subject to the impulse with 0 initial velocity, with the 0 initial conditions, and after that one, they have the equivalent description like this. Keep this in mind. Okay? Good. So really, we solve for this. We're going to solve for this function. Actually, is we're going to solve for this problem. So the solutions, the response of the system with such initial conditions will give us the GT. Okay? And I'd like to solicit any questions before I move on. So to this step here, we have quite a bit, a little bit few more concepts and imposed to you. First one is the introductions of the impulse function, unit impulse function, and the second one is take up the dynamics. Okay. Okay. So if without any questions, let me erase this one. Do you know how to solve for this? Chapter 2, right? And that is we look at this description, this is the free vibrations. Free vibration with initial velocity, initial conditions only. If you still remember, for the free vibrations and for underdamped system, we have xt. For example, the characteristic CHARAC, the root, equal to minus zeta omega n plus minus j omega n 1 minus zeta squared, right? So that is zeta omega n plus minus j. We define using omega b, right? So if you remember this one, then the solutions equal to E minus. So this is the real part, and this is the imaginary part. So for this response is exponent, and that is the real part here, minus zeta omega n t. This term provides, again, here is a review. the profile of the decay that is provided by such a term, right? And then this is the underdamped system in oscillations, and oscillation is given by the frequency, the damped frequency, right? So that is in A cosine omega dt plus B sine omega dt. Will that be okay? Have I helped you recall your memories on this? Good, right? And that is part of a homework exercise. I forgot which one, 3 or 4 there. You good? Okay, so A and B are the two unknown constants that can be determined by the initial conditions. So we focus on here. So here we can calculate so this is the magnitude. So A, B are determined by initial conditions. So from here, the x0 equal to 0. So from here we can say, you can see A is equal to 0 right away. You set up the time, introduce time and t equal to 0 to these equations, and sine 0 is gone. And this becomes 1 times A times cosine 0, so that is 1. So here A equal to 0. Okay, so for this case A equal to 0, so let me knock out this term. So in this way we have xt, because the black powder currently in out. So therefore xt equal to b times e minus zeta omega nt and sine omega dt. So here we can calculate x dot velocity, and this one needs a little bit of calculations. So that will be equal to b times minus zeta omega n and e minus zeta omega nt sine omega dt plus e minus zeta omega nt omega d times cosine omega dt. Okay, because here there's a multiplication of the two time functions. So when we do the derivative, we do the partial derivative to each term, so like this one. So therefore, we know the x dot initial velocity on one side equal to 1 over m here. Okay, on the other side, we plug into these equations, and that will be equal to omega d, right? So therefore, d equal to m omega d. Good? So from here, therefore, we have xt will be equal to this one, 1 m omega d and exponent minus zeta omega nt and sine omega dt. I know there's a long writing in terms of the symbols, but once you work on the numbers, that should be very quick. But okay? So the whole solution process, don't be scared, don't be overwhelmed by those by the kind of writing. But the concept is we solve for this one. Be good? Okay? So this represents the system response to a unit impulse. And this unit impulse applied at time 0. So that means GT for this case simply is this one. So GT is response to this, right? So right now, if you have your lecture notes and turn a few slides, turn a few pages back, the backward. So right now, I'm going to write down the GT. GT is a response of the system to such impulse, which is not unit. For this impulse, it has the magnitude equal to this. So again, for these functions, let me write it up here. This one here, I've been written up here. Okay, so this is similar to the impulse, but this one has a magnitude. So this is a magnitude, and that's an impulse. So basically, the GT simply is the, if you remember, from the beginning, our derivation is due to unit impulse. And right now, for our case here, it's not unit, it's a magnitude with such a case, right? And if you remember, if we are dealing with the non-unit impulse function, we simply scaled up the result by appropriate magnitude. So basically, the GT will be taking this pattern, but we scaled up by the magnitude here. Okay? You know what I'm saying? No? Okay. We can do it again. So keep everything here. Let me turn off this one a little bit. Let me bound this. So this is our template. So right now, let me build up the case for that, and we can redo it. So let me redraw these things from there. So this is the t, and this is our function of time. Okay, and right now we are dealing with the pulse function. This pulse function is equal to f0 times delta t, and this is the delta t, and this magnitude equal to f0. So its area equal to the height multiplied with the width equal to this one. And this is a pulse-like function and with a magnitude. So if really we can say that is the unit is a magnitude of this one. So basically it's a pulse function. So for the systems, right now we want to get the result. So system, so that is the system response. Okay, so the system response is coming from here. Mx double dot plus Cx dot plus Kx. And compared to our generic calculations, and right now the force totally equal to this one, F0 delta t times delta t. So this is the magnitude of the pulse function. Compared to this one, you can see that simply is the force being scaled up by such a factors, right? So that means this one you can see compared to this. So again, that is equivalent to systems. Again, right now I kick these tables with not a unit pulse, but with this one. So that means the initial velocity will be equal to not 1 over m. 1 over m is for unit impulse, but here the magnitude is that big, so that is this one. This simply is the magnitude of pulse. Okay? Yes? Good? Okay. So right now you can see compared to the both calculations, the initial velocity being scaled up by this. So if we would repeat the whole calculation, eventually we should have a similar result. let me pick up the pattern. M omega d, and scaled up by the same numbers. And sine omega d. You good? Yes or any questions? Good? So that is given by this. Okay? Compared to our generic, this is the systems. Okay, so this generic formulation we call the system is under unit impulse excitations. So the system response to the unit impulse excitation, that is this answer here. And here we have a particular name, and this is simply called the unit impulse response. Okay, that is a very special keyword, and if you adopt this one, you should be able to get it from many places. If you type in the unit impulse response, and you can get it. And in our textbook, and it using the very special notation GT. GT is the symbol for denoting unit impulse response. So the people ask you what is a unit impulse response, you're simply saying vibration systems is under this excitation, that is a unit impulse. That's it. So using this notation, you can see for this case, this basically is equal to the magnitude multiplied with GT. You good?